Okay, Hey everyone. The topic of this talk is why latency is the number one metric of your clouds and not some other thing, right? So who am I, and why am I talking about this stuff? My name is Bojan Krosnov. I'm the chief of product of a software-defined storage company called Storpool. And previously, in a previous life, I used to do packet processing and kind of what later became called SDN. But since 2011, we're working on Storpool and nowadays growing that rapidly. Storpool is a fast and efficient software-defined storage system. It's used by public clouds and private clouds. And it's a clean slate design, meaning we didn't step on some open source project. We wrote the whole thing from scratch, right? It's mostly used with KVM, although there's some Zen server and VMware and Hyper-V. And it's mostly used with deep integrations into OpenStack, Cinder, and Kubernetes and other orchestration systems in this open source ecosystem. So first to explain why, to understand why, not just give you some numbers and make you wonder about them. Here's how all transaction processing systems behave in terms of performance. If you have a small load, you get low latency. If you increase the load, you get increased latency, right? And you don't get a lot higher latency when you increase load, up to a point. So if you have one task on 4 CPU cores, say that task takes 1 second. If you do 2 or 4 tasks, it still takes 1 second. So you get 4 times more tasks per second completed, right? And the moment you get more tasks done, units of processing than CPU cores in this case, not only didn't you process more tasks per second, you still processed 4 tasks per second. However, you also slowed down the original 4 tasks. So all of these tasks took a longer time. You didn't get a higher throughput. So all transaction processing systems, which is databases, storage systems, load balancers, web servers, all of these systems have something called a saturation point. And if you try to put more load on them than they can process, you're running them in what's called congested mode. So they have 2 very different modes of operation, 2 different ways in which they work. One is the elastic mode, where in elastic mode, if you put more load on the system, you get more work done, right? And in congested mode, if you put more load on the system, you don't get more work done, right? So it's a very different behavior. If you're running a kind of a complex application, to get the best end user experience, what you want to do is you want to run all of your systems in this part of the curve, meaning you have systems that have kind of huge throughput, and you run them at 1% of their throughput. The load you put on them is like 1% of the throughput. However, that's not very cost optimal, so people tend to run their systems up in that end of the curve. So to get the best cost per delivered something, per delivered web page or something, you want to run your systems in that part of the curve. And obviously, somewhat, the problem with running your systems in that part of the curve is that the moment you get over the knee, it's very painful. It's very painful because the whole thing grinds to a halt, and you get not just slightly increased latency, you get infinite latency because things start piling up in queues, right? We call this parameter of these systems, we call it the system throughput. So how high the saturation point is, right? Well, when a software vendor or a kind of a system vendor, when they brag about the capability of their system, mostly what they're talking about is this end of the curve. And if you care about application performance, that's totally irrelevant. Why is it irrelevant? Because you don't run your applications in that part of the curve, right? You always run them in the elastic part of the curve. And you want to know how that system behaves in the elastic part, not how it behaves in the congested part. The congested part is mode is kind of obvious how it behaves there. All right, so I have a small demo to show. And it's designed to convince you that that IOPS number you get for a virtual disk is completely irrelevant, right? So it has some meaning, but it's not what drives application performance, right? So we have a virtual machine with 2 virtual disks. One of the virtual disks is a fast virtual disk with about 0.15 milliseconds of latency. And the other one is a slower virtual disk with about 2 milliseconds of latency. The way we achieve that is they're on the same storage system underneath, but for one of them we've added kind of artificial delay with a device mapper module called DM delay. And both of them, if you kind of perform a 4 kilobyte IOPS benchmark on them, both of them will measure 20,000 IOPS, right? So this is 20,000 IOPS, and what we vary is where the curve starts. One of them, it starts at 2 milliseconds, the other one starts at 0.15 milliseconds, right? It doesn't tell you how the whole curve looks like, but it's just one kind of metric of how the performance of that system looks like. How are we going to show application performance? We're going to use pgbench, which is a database benchmark for PostgreSQL, on a database which is 4 times the memory size, and it's not that big of a database, really. It's like a 60 gigabyte database. These parameters for pgbench, they weren't chosen randomly. They're based on kind of an established way of measuring the performance of PostgreSQL. All right, so let's see if the Chinese internet will allow me to do a demo. Just 1 second here. So this is a latency measurement of the volume we are running on at the moment, and it says about 2 milliseconds for reads, 2 milliseconds for writes. This is an IOPS measurement of that. And you can see, like, yeah, so like 10,000 reads plus 10,000 writes, total 20,000. If you do this is pgbench running on top of a PostgreSQL database on this volume, and you can see it does, it has a summary somewhere like 1,800 transactions per second at a latency of about 8 milliseconds. If you have a database that can only do 1,800 transactions per second, if you try to if you have a higher load, if you try to ask it to do more, what you'll get is a pile up. So you'll get this kind of transactions taking 3 seconds now, and they take 4 seconds now, and etc. Right? So if you try to ask a system that's not so capable of more, you get a pile up, right? So if we switch to the other one, this is the volume with the, give it 5 seconds to just run the quick benchmark. This is a volume with about 160 microseconds, sorry, for reads and 120 microseconds for writes. And it also measures 20,000 IOPS, I think. There it is. So it's about 10,000 reads plus 10,000 writes, about 20,000 IOPS. If you ask it what would be the performance of a PostgreSQL database on that one, we get about 5,000 transactions per second, right? So obviously, if you ask a database that's capable of doing 5,000 transactions per second, if you ask that to do 2,500 transactions per second, it's pretty happy doing that. You know, it does that at like 3 milliseconds latency per transaction. So what this means is if you go to a public cloud operator, say AWS, and you buy a volume that has 20,000 provisioned IOPS, you go to another operator and you buy a volume with 20,000 provisioned IOPS, these are not the same service because the specification is incomplete, meaning they didn't tell you the most important parameter of the service they're providing, right? So, say, you know, if you the 2 millisecond gets 1600 or 1800, and the 0.15 millisecond volume gets a lot more transactions per second. And public clouds don't publish these numbers, so the only way to get them is kind of buy a service and measure it, which is what we did. And on various, you know, some places are higher, like 1.7 milliseconds, other places are 0.7 milliseconds, say Tencent Cloud here in China. And we can say that DigitalOcean is doing a pretty good job at running Ceph, right? They have a large-scale deployment. They have the best engineers in the world. You know, they're trying to do their best, and they're getting about 1.7. The problem with these numbers is that they're not very competitive in the market. So things like Alibaba Cloud here in China or AWS can do a lot lower latency. So as an application developer, if I start building my application on, say, I don't know, DigitalOcean or OVH, I put my database there, I start gaining users, and then at one point in time, I realize that it's just not economical, it just doesn't work. I go to AWS and things start working. And people just are amazed and they don't understand why. This is why. Because the latency of the storage systems is different. The last one is obviously one of our customers, and they've built their cloud based on our recommendations. So they follow, like, they get the right kind of hardware, they configure the network in the right way, etc. Right? This is the same kind of benchmarks, PGBench on various public clouds, including the store pool best current practice. So the message here is if you're using a store pool storage system, you will get database performance that goes like this, right? And if you're using Ceph, you'll get database performance that goes like this, like the blue dots here on the bottom. So this chart is transactions per second versus latency for PostgreSQL transactions, right? And this was my prepared material. Let me know if you have any questions. I'm really open to hearing what you guys think about this. Okay, sure. The question is, do we have a business case comparing AWS prices versus investing in our software? We know from experience, based on our kind of largest customers, that when you take the cost of the hardware and the cost of store pool and their margin, which could be like 50%, right? They're still able to offer a storage service, SSD-based storage service competitive with AWS, which means at, say, 10 cents per gigabyte per month, right? So the business case works. Like you can get this kind of performance, a store pool kind of performance for the cost of AWS kind of cost per gigabyte per month, right?
Yes, thanks. Looks impressive, but maybe you can share information about scale, how this number is related to scale. So, of course, for customer, it doesn't matter
Yeah.
what is scale for in public cloud, but for service provider, it's matter. So, like how we can compare DigitalOcean scale with this store pool scale
Yeah.
on this chart.
Right. So first, kind of a massive disclaimer. The numbers on this chart, we are fairly limited in our testing methodology here. So the best we can do, because we don't have kind of internal access to DigitalOcean, right? The best we can do is we can go and buy a virtual machine there, and we can measure what we see inside the virtual machine. We can go to our customer and get a virtual machine there and see what we see inside the virtual machine. For our customer, we know how they use that cluster. We know kind of the load in that. And for our customer, I can say the specific guys have about a petabyte of data in that cluster. And it's about 80% full. It's a typical kind of web application thing. So they kind of both sell virtual machines to their customers as well as run MySQL databases and email and all the kind of the mixture of a web hosting company. In terms of how you can scale this to tens or hundreds of petabytes, what you do is you take that 1 petabyte deployment and you repeat it, and you will get the same kind of performance inside of each of these deployments. Generally speaking, you wouldn't build a single system that's tens or hundreds of petabytes because it doesn't make too much sense, right? The biggest problem there is you're putting too much eggs in one basket, in one system, and you want to separate them somehow. And this is it's only logical separation, meaning from end user's point of view, they come and buy a virtual machine, you don't need to tell them it's 10 clusters underneath, right?
Half of petabyte, correct? This scale.
It's about 1 petabyte, yeah.
1 petabyte, okay.
Yeah.
Thank you for answer.
Thank you all.